there are few things which I have left in real scalar field. Those I will take after this complex, because the analysis of those points will be same. Only the name changes. One is complex, another is real. Okay. So in the real field, real scalar field, how many particles it what? Okay, how many degrees of freedom are there? Okay, so let's put this way. How many types of particles it describes? Only one field, because real scalar means real. It's only a single quantity. Okay, although it describes infinite number of particles, but the kind of particles is only one. Clear? Only one type of particles. Okay, so now if I take a complex scalar field, we will see it describes actually two particles. Okay, because okay, so complex means it is having two real components. Okay, if you are having a complex number z equal to a plus ib, a and b are real numbers, is it? So similarly here, let's say you are having a complex field sum phi, you can decompose it into real and imaginary parts. Okay, let's say phi 1 and phi 2 both will describe the particles. Okay, so that means the complex scalar field will describe you, okay, two particles at least. Clear? Got my point? So this you should know, you should bear in mind. Okay, so now let's say for the complex scalar field, the Lagrangian is given by this thing. So I will write this way. Okay, so this is a Lagrangian for a free complex field. Okay, I am not considering any kind of interactions. Okay, so now let's take this phi and decompose this phi into two fields, phi 1 plus I, phi 2. Okay, so I can decompose it. Right? Okay. So what does it mean? Okay, so if you are having this, now let's calculate the equation of motion first. So what are the equations of motion here? Okay, you can calculate equation of motion. Okay, so let me write for each type of field, partial mu, partial L, partial mu phi, okay, minus partial L by partial phi, that's equal to 0. So let me put an index A here. Index A means what? Two types of fields. Okay, for A is equal to, let's say, phi or phi dash. Clear? So it will be something. For phi it will be partial mu phi. For phi dagger it will be partial mu phi dagger, because you are having two fields here, phi and phi dagger. Okay, you are having an equation for phi as well as its complex conjugate. Clear? Okay. So if I take now for phi, so one equation will be like this thing, nebula plus, this box operator, m square, it is equal to 0, and you are having two kg equations governing the dynamics like this thing. Clear? Okay, so you will be having kg equation for phi as well as for phi dagger. Clear? So these are the classical field equations. Okay. Now let's find this phi in terms of this phi 1 and phi 2. Phi 1 and phi 2 are real quantities. Clear? So these are the real fields. Okay. So now let's substitute it in this thing. So your Lagrangian will be, so it is partial mu phi 1 plus I phi 2 like this thing, and then you are having partial mu. Now what is the phi dagger? It will be phi 1 minus phi 2. Clear? Okay, so what is your phi 1 dagger? That is same as phi 1. If there happens to be any confusion, it's phi 2. They are real quantities. Okay, minus m square phi dagger is phi 1 minus I phi 2, and another is phi 1 plus I phi 2. So now how it looks like? It simply looks like partial mu phi 1, partial mu phi 1 plus partial mu phi 2, partial mu phi 2, okay, minus m square phi 1 square, okay, minus m square phi 2 square. So it is simply the sum of Lagrangians of two real fields. Clear? Okay, so this is simply, okay, so this is the Lagrangian of real field of phi 1, this is the Lagrangian of the real field phi 2. Clear? So therefore I can write Okay, I can write this L as some sum of, let's say, n is equal to 1 to 2. Okay, so but there, sorry, I should have put actually 1 by root 2 here. Put 1 by root 2 here, you will get 1 by 2 here and 1 by 2 here. Clear? So this is the proper way to do it, normalize it way. So you'll be getting like this thing, half of partial mu phi, let's say n, partial mu phi n minus half of m square phi n square. So that means okay, now you have seen if, let's say, one real field describes one type of particle. So you are having two real fields, they will describe two types of particles. Clear? Got it? Okay. So now we can do the quantization as the way we have done for the real scalar field. So it is now easy. Clear? Any question? Any question? Okay. So now let's figure out the conjugate thing. Let's calculate the conjugate momentum. Momentum corresponding to, let's say, phi 1 field. Let me call that as phi 1. What will be that? That is simply phi dot 1. And the momentum corresponding to phi 2 field, that will be simply phi 2. Clear? Okay. So you have to calculate it. Okay. So what is the formula? Pi is equal to partial L by partial naught phi. So this is the formula. From this very formula you calculate it. Pi 1 to be phi dot 1 and pi 2 to be phi dot 2. These things we have been doing all the time. Clear? Okay. So now let's try to quantize the things. Okay. So how to do the quantization? So now let me quantize this complex scalar field. How to do it? I will simply quantize what? Each field. Clear? So since it is simply the sum of two fields, so I will put just a quantization condition for each field. Got it? First tell me, is there any coupling between the two fields? Is there any coupling? Coupling means is, let's say, you are having phi 1 here and phi 2 here. Okay? You don't have the cross terms, the mixed terms. You have only the free terms. Free terms for phi 1 and the separate terms for the phi 2. Clear? You don't have any term that is multiplying phi 1 and phi 2. Clear? So that is okay. So that what I mean by you are decomposed actually a complex scalar field, free complex scalar field without any kind of interaction into the sum of two real fields. Okay? Got it? Okay, so now if I have to quantize my complex scalar field, what I will do? It is okay, simple to quantize free fields. I mean these real fields separately because there is no coupling between the two. Clear? So what for that matter, what I will do? I will choose this equal time commutation relations. So I will impose then. So you are having phi 1, let's say xt. Okay. Then you are having this phi 1 yt. So this has to be equal to I delta 3 x minus y. So at equal times it should be like this thing. So these are the quantization conditions. So it is I delta 3 x minus y and all other commutators. Since there, okay, phi 1 is independent of phi 2. Okay, look at this decomposition. Both are independent of each other. Okay, so then I can say you don't have any. So phi 1, phi 2, that's equal to 0. That is same as, let's say, phi 1. Okay, phi 1. Okay, phi 2, and that's equal to what? Phi 2 pi 1, and that is same as what? 0. I mean all are 0. Phi, okay, so pi 1 pi 2. So all these commutators are 0. Clear? So now we have figured out the quantization condition. Now what I have to do? Let me try to decompose my fields in a Fourier extension. Let's figure out the Fourier extension. Clear? Okay. Let's have Fourier decomposition. Okay. So everybody got this equal time commutation relations? Okay, last time I have told you equal time commutation relations describe you the quantization condition. Clear? Okay, since you are having each field, you are having two fields. For each field, I have described separately. Clear? Okay, so now let's do the Fourier decomposition. Okay, for real scalar field, okay, I am having what is the Fourier decomposition? D3P divided by twice EP, okay, A of P e raised power minus I P dot x plus A dagger P e raised power I P dot x. So this is for the real scalar field. Okay, how many fields we are having here? Two fields, correct? So let me put some index I. Okay, I is going for each field. I am having this thing. So let's write it as I. Let's put an I here. Clear? So each field have this kind of decomposition. Okay. So, but I don't require the decomposition of phi 1 and phi 2. I actually require the decomposition of phi and phi dagger. Okay, because ultimately I have to look at how phi looks and how phi dagger looks. Clear? And we need to figure out what the particle interpretation of the fields. Clear? Got it? Okay, so let's try it. So what is our phi of x? So that is simply phi 1 plus I phi 2 by root of 2. Clear? So let's write it. Everybody is satisfied? Okay, so now what is phi 1? So I will write, okay, d3p by root of 2 pi. Is it visible? Okay, good. Then I am having, okay, look here. Integration is same for both fields, clear? Phi 1 and phi 2. What you are having? You will be having A1 and A2. So can I write it like this way? So you are having A1 of P plus I A2 of P. Can I write? Divided by root of 2. There is root of 2. Can I write it? Is this the sum of these two terms? So it is A1 plus A2. Phi 1 plus phi 2. Clear? And e raised power minus I P dot x plus another will be A1 dagger of P, then plus I A dagger 2 of P by root of 2 e raised power I P dot x. Clear? This is phi. Okay? No, it is plus. Because it's plus, look here. You are having what? Okay, A1 and A2, you are having A dagger 1 and A dagger 2. A1 plus I A2, A dagger 1 plus I A dagger 2. Got it? Okay, so now let's calculate the conjugate. Therefore, I can write this phi dagger of x. Okay, so what is that equal to? D3P divided by root of 2 pi cube twice AP. So what that will be? So it will be A1 dagger P minus I A dagger 2P, okay, divided by root of 2 e raised for I P dot x, because I am taking the dagger, okay. Then so it will be A1 of P minus I A2 of P by root of 2 e raised by minus I P dot x. Okay. Now let's look carefully at this very expression. Okay. Let's look carefully. Okay, look at this very for each real field. Okay, for real field I am having this kind of expansion. This object is conjugate of this thing. So if you say this as an annihilation operator for a particle, you call this as a creation operator for the particle with the momentum p. Clear? Got it? So these two are conjugate things. But look at these two expressions. So you should have expected this object to be conjugate of this thing, but they are not. Now take it is dagger. What you will get? So look here, the dagger of this entire thing gives you this thing because phi is real. Clear? So but the dagger of this entire thing is not this thing. Look here, if you are having A1 dagger is there, but I should go to the minus. What you are having? Plus. Now look here. So you are having the term, the conjugate for this term is this thing. Clear? And the conjugate of this term is this. समझ रहे हो?
Yes, sir.
You got my point. The reason for this being because you are having two types of particles. Because phi, this complex phi describes you two types of particles. Clear? That's why you are having one type of particle described by this thing and its conjugate like this thing, and another type of particle described by this thing and its conjugate this thing. Okay? What is phi? Okay, tell me, what is phi plus phi dagger? That should be a real quantity. Is it? Is that true? Phi plus phi dagger is a real quantity. Can you get the real quantity from here? So you will get actually the real quantity. So, समझ आया? Okay. So what I will do, I will introduce. Okay. So new type of operators. Let me introduce an operator A of P as A1 of P plus I A2 of P divided by root of 2. Okay. And I will introduce another operator B dagger of P as A1 dagger of P plus I A dagger 2 of P divided by root of 2. Clear? Got it? Okay. So what I have done, I am just writing this thing by an operator A of P. Clear? Then I need to figure out what is the interpretation of this A and B. Got it? So if I am writing this object as A of P and this I am writing as B dagger. Okay, so what this will be? So this is A, this is B dagger. So what this will be? So this will be therefore A dagger. What this will be? B dagger. Sorry, B. Clear? समझ रहे हो? So let me rewrite this thing. Okay. So therefore we will write Fourier decomposition of complex scalar field as so it is A of P e raised power minus I P dot x plus B dagger of P e raised power I P dot x, and you are having this phi dagger of x as d3p by root of 2 pi cube twice EP. So I will write this thing first, B of P e raised power minus I P dot x plus another I will write as A dagger P e raised power I P dot x. Clear? So now A will represent one type of particles and B will represent another type of particles. Clear? Got it? Okay, so what will be now the home assignment for you people is, so you figure out A and B in terms of phi and phi dagger. Clear? Okay. So assignment is okay, figure out A and B in terms of phi and phi dagger. Clear? And then show that you are having this is the commutation now. Yeah, P A dagger of P prime. Okay. So this is equal to delta 3 P minus P prime. Okay. Clear? And then you are having B of P B dagger of P prime. So that's again what? So the quantization condition what you are having, so they will translate like this thing. समझ आओ? Okay? And all other commutators are 0. All other commutators are 0. So what? Okay, so commutation between A and B, what I mean by commutation between A and B is equal to 0. So that means they are independent particles. Got it? Any question? Now we need to figure out what is the interpretation of this A and B. Okay? So let's calculate. So you can calculate now the energy of the okay. So let's calculate the Hamiltonian. So that is d3 of x. This Hamiltonian density, what is that equal to? It is d3 of x. What it will be? Pi. Okay. So you will be having how many pi's you are having? 2. So you are having pi dagger plus pi, okay, phi dot dagger. Okay, so this is a pi corresponding to phi. This is a pi corresponding to phi dagger. Clear? You got my point? Minus. Yeah. Since there are how many fields? So it is something like this: summation of I p q dot pi q dot r. Clear? So for each q you are having what? Momentum. So for phi you can calculate the momentum pi and multiply by what? Phi dot. Then you calculate the conjugate momentum for phi dagger and multiply by phi dot dagger minus Lagrangian. Okay? So what you will get ultimately, then the Hamiltonian will be like this thing. Okay, can anybody tell me? Can anybody? So it will be simply, okay, phi dot dagger, okay, then plus del phi dagger, okay, plus m square phi dagger phi, this thing. So in other words, it is something d3 of x, okay, mod of phi dot square, okay, plus mod of gradient of phi square, okay, plus m square mod of phi square. Okay, so I have given you the prescription in the last lecture how to calculate these things. So now you are having an expansion of phi and phi dagger. So calculate phi dot dagger and multiply and integrate over x and take these terms. So you will get ultimately the energy in this form. So this will be the home assignment. So you will get the energy integral d3p. So you will get EP 8. So I mean the normal order kind of thing. A dagger of P, A of P plus B dagger of P, B of. So this is the normal order Hamiltonian or the energy. Clear? Got it? Okay. So you have to use these very commutations to get the normal order thing. Okay. So now let's calculate one important thing. From there we can interpret. Okay, so now you can interpret. So you can make the commutation between H and A. You can say A dagger is the creation operator for particle type A, and A is the annihilation operator for particle type A. Clear? And B dagger will serve as the creation operator for particle type A, and B will be the annihilation operator for the particle type B. Sorry. B. Clear? So in other words, you are having this as the number operator. So you can be having, let's say, number operator corresponding to type A particles A dagger P, A of P, and for B type of particles, okay, so let's say Na, so let's write this as Nb, so it is B dagger P, B. Okay, so that means if you need to calculate the what is the total energy in the system, okay, what is the total energy contained in the field or the stored in the field, so it will be the contribution from the total energy due to A type of particles and due to B type of particles. Clear? So suppose if you can think it this way. Suppose I am giving a one-dimensional box or some box, and there are two independent particles, and you are asked to figure out what is the total energy of the system. What you will do? You will calculate simply the energy of one particle and the energy of the other particle and add it. Okay, if there are no interaction, if they are simply free. Clear?
But there is a terms of coupled energy term.
Where? No, there is nothing coupling.
The third step, this phi dot and phi dot dagger.
No, this is not the coupling. So you have to calculate it into, this is simply the this Hamiltonian, okay? This is not the coupling. So you have to calculate phi dot and phi dot dagger from here, okay? And substitute in this formula, and you will put ultimately it in terms of A dagger and A. Clear? Got it? Okay. So let's take another point from where we can actually interpret these things. Okay, okay, we can say this A represents, let's say we will see actually A type of particles, this represents particles, and this B represents the antiparticles. Okay, we'll see it in a moment. So if you are having a theory that comes with the pair of particles, that means one particle is having one set of quantum numbers. Okay, in order to conserve the, let's say, in order to have a conservation rule in a given system of the conserved charge, what we are going to see. So if you are having a particle, if your theory comes with, let's say, two types particles or a pair of particles, the one type of particle has actually, let's say, if it has one set of quantum numbers, the another particle will be having an opposite set of quantum numbers. Clear? So that the total, you don't have any kind of, so the total number is conserved, I should say. Clear? Got it? So you can be having, when a theory comes with the pair of particles, you can always treat one type of particle as this particle and the another as antiparticle. So that means there will be always a particle antiparticle. Okay, let me give an example here. So we started with the real scalar field. Clear? So for real scalar field, you don't have any antiparticle because particle and antiparticle are the same in that case. Okay, think of the pi naught. Okay, so you are having three scalar particles, pi plus, pi naught, and pi minus. Okay, so this is chargeless particle. We describe it by, let's say, phi field. Clear? And these two types of particles, they are actually antiparticles of each other. What is the charge here? It is the 1 unit and 1 unit positive, and this is the 1 negative unit. Clear? And if you see all the properties, their properties are actually opposite to each other. Okay, these are the scalar particles. Clear? Okay, scalar particles, scalar charged particles. You can describe them by this real scalar field. Clear? Got it? Okay. But if you are having electron and positron, you describe that by the Dirac theorem, because electron and positron, they are the fermions. Here we are doing with what? Scalar particles. Okay. Okay, so now let's take. Okay, so let's look at the conservation rule for this thing. So you are having this very homogeneous. Okay, so we'll do this field in detail. We'll see how the gauge coupling arises. Okay, how the matter field, how gauge principle guides us to, how gauge principle guides us for the interactions. Okay, how the gauge field emerges. Okay, and there is a coupling between matter and the gauge field. Okay, it is actually the gauge principle which will help us to guide. Okay, that we are doing when we'll take symmetry in detail. Okay, so now let's look at this kind of symmetry. So if I change this phi by, let's say, some phi prime, that's equal to e raised power minus I q. Let's assume q is the charge on the particle and theta is a parameter, theta. Okay, and make this kind of transformation. It is simply phase change. Okay, if I am making simply a phase change, what will happen to this very Lagrangian? It does not change at all. So if you look at this very thing, what is the transformation rule here? This is the transformation matrix which changes your phi to phi prime. Clear? Although it's a number, because theta is a number here. Okay, it's a single parameter and it does not have any kind of dependence on position or time and so on. It is simply a constant quantity. E raised power minus a minus ia kind of thing. So that's always a number. Clear? So let's say if you take theta from 0 to 2 pi, so you are actually on a unit circle. Okay, so this kind of group we call as a U1 group. So you are having this as a U1. We call it as a global. Global in a sense. So this theta does not, this parameter does not depend on any kind of coordinate. Okay, so it is same everywhere. So you got my point. So what is the value of, okay, so this U1 group is given by this e raised power minus I theta, okay, where theta is from, belongs to 0 to 2 pi. Clear? So it takes all these numbers. So in other words, I can say this Lagrangian possesses what? U1 symmetry, global U1 symmetry. It is sometimes known as gauge transformation of first kind as well. Okay, so since we'll see when we put this theta to be the function of x, let's say, then you will see what this gauge means. Okay, for the time being, we'll just use it is simply global U1 under global U1 transformation. This Lagrangian is invariant. Okay? It possesses this kind of symmetry. Samajh? Okay. So now if you see, okay, so if you look at this thing, it includes actually a circle of unit radius. So it is simply the circle of the unit radius. Is it? What is the radius of this very circle? So e raised for, it is simply z is equal to r e raised for I theta. Clear? So what is the radius? Mod of z is equal to r. Clear? But here what is r? That's equal to unity. So that means, so the group space here, since this is a group, okay, all the elements on this very parameter, they form actually a group. Clear? So all the elements from 0 to 2 pi, if you see, they form a group under multiplication. So you can multiply. So this is a group under multiplication. It is actually a single number, if you see. These are all only one element. These are not matrices. They are only what? One element. Only one element. So you are having, let's say, take theta is equal to 0 here. What you will get? 1. Clear? And let's say take theta is equal to pi by 2. What you will get? I. So these are all the possible values of this very set, and they form a group under what? Multiplication. So that's why we call it as a U1 group. Now tell me, what is the space? Okay, so if I look at the area of this very circle, is this finite or infinite?
Finite.
It's always finite because the radius is equal to unity. In this sense, okay, I can say this is actually a compact group. Okay, so this is a compact U1 group. Clear? If the area under the group space is actually the finite, this is the simplest way to understand it, to understand the compactness. So this kind of group is compact. Take off the rotation as well. So this actually this is simply a phase rotation of the wave function, you can say. Let's think the rotation in 3-dimensional space, the O3 group, what we have studied. So what are the parameters? All the parameters take the value from 0 to 2 pi, is it? So what is then the volume covered? So that is actually the transformation on the sphere, is it? What is the volume of the sphere there? So it's again finite, clear? Or the volume of the group space, that's again finite. So that rotation group, you can also say it is a compact Lie group, clear? So this is also the compact Lie group. Now if I take the Lorentz group in general, so Lorentz group is not actually compact. That's a non-compact group. Clear? Because you are having one additional parameter in addition to the these angles, you are having what? Speeds. Okay? So that makes it non-compact. Okay, so this is just maybe in literature, you are in books, you will be saying compact and non-compact to just make you understand what exactly these terms means in a simplest way. Okay, so now what will happen to this phi diagram? Okay, so if this remains invariant under this thing, now tell me, is this a continuous symmetry? Is this a continuous group?
Yeah.
It's a continuous group. When I say, okay, so I am saying, so under this transformation L is invariant. Okay, so this is a continuous transformation. Now you have to invoke the Noether theorem. Noether theorem says when you are having a continuous global symmetry, so then you will get a conservation law. Okay, you will get a conserved quantity. Clear? Okay, so we need to figure out what is the conserved quantity here. Samajh aaya? Okay, so you are having by Noether theorem. Okay, so Noether theorem says, so you are having now the conserved quantity. Yes, question? Okay, so let's try to figure out what is the conserved quantity. So what is the conserved quantity? So that is the let's calculate first the Noether current. Okay, so what is that? So you are having partial L by partial phi, partial mu phi, is it? Then you are having delta phi. How many fields you are having? Two fields. Let's write this delta phi dagger, partial L by partial mu phi dagger. Okay, got it? So since you will be having two terms, then anybody minus that delta x nu, okay, t mu. Okay, is it? So this is your current in terms of this energy momentum tensor. Okay, now look at this very thing. So if I am making this kind of phase rotation, and this rotation does not depend on x, and it does not involve, this kind of phase rotation does not involve any change in coordinate, clear? So that means I am having in our case this delta x is equal to 0. Clear? So that means this will not contribute. Okay? So what contributes ultimately? These two terms. Okay? So now let's calculate this delta phi. What is the variation in phi? Okay? So what is your delta? So let me calculate. So your phi prime is actually equal to e raised. So this is the infinitesimal change, is it? Delta phi. So what will be the infinitesimal change? So I will write it as 1 minus I q theta and phi. Clear? Can I write it? So just expand it. So which implies therefore the small variation will be simply equal to minus I q. So it's with respect to theta. Okay, you can put parameter equal to 1 at that. It's a number purely. Okay? It is not a function. So this is your variation. Okay? So now tell me what will be therefore this delta phi dagger. Sorry, it is delta phi, not delta phi prime. What will be delta phi dagger? Because it's phi prime minus phi. Okay, divided by theta you can say, and theta tends to 0, but theta tends to 1. Okay, so it will be I q phi dagger. Clear? So therefore what I can write? So let's write this G mu is equal to partial L by partial mu phi. So it will be simply partial mu phi dagger. Okay, if you calculate this thing for your Lagrangian, okay, now let's calculate. So this will not contribute, your this will remain there, is it? Okay, so this will remain there. So what is delta phi? It's minus I q phi. Then you are having plus delta phi dagger I q phi dagger. Then what is this partial L partial mu dagger? It will give simply partial mu phi. Okay? Okay, so therefore I can write this G mu, it is as minus IQ, let's take it out. So what remains there? So it's partial mu phi dagger, then you are having this phi, then you are having this minus phi dagger. If you remember, sorry, it's partial mu up. So sorry, this index is up. Partial mu phi. Okay? So if you remember, we calculate actually the current in the Klein-Gordon, and we are doing the Klein-Gordon equation, is it? So what is Q here? Let's interpret Q to be the charge. Okay? Charge on the particle. Okay, so let's calculate what is the Noether charge. So this is the Noether current. So let's calculate the Noether charge. So that's Q is equal to integral d3 of x, J is 0 of x. So this is a conserved quantity. Q is also a conserved quantity. Clear? Noether charge is a conserved quantity, is it? So what is now J0 of x? So you take minus IQ out, integral d3 of x. What is J0? It will be partial 0 phi dagger. So that is simply phi dot dagger and phi minus phi dagger, and it will be phi dot. Okay? So this is your Noether charge. Clear? So now from here you proceed yourself onwards. You know what is your phi by Fourier extension, and you know what is phi dot. Okay, because you can calculate phi dot for that and take the dagger. Is it? Got it? So you know phi. You have to make those things you have to do yourself. Okay. Okay. So what you'll get? So it's minus IQ. Ultimately you'll get like this thing, d3 of Q, d3 of P, like this thing. Okay. Okay, so I will write now this as the normal ordered object. You'll get like this thing, A dagger of P, A P minus B dagger of P. So there are many steps you have to do it. You have to do yourself, because I have shown you how to do it in the last lecture. Okay, you have to use what? What is phi? Okay, and you take phi dot, then take dagger, multiply the two, and integrate over x. Clear? So you will be having an expression in terms of A and B. Clear? And similarly, you will be having for this thing. Subtract the two. Okay. So ultimately, what you will get? You will be getting actually A dagger, A minus B dagger. Clear? But I am using what? I am using normal ordering. Clear? Normal ordering means you just put annihilation towards the right of the creation operator. Clear? So you will be getting like this thing: A dagger A minus B dagger B. Okay, so now what this represents? This is a number operator for the particle type A. So it means when you integrate over momentum, what it will give you? Total number of particles of type A in your system. Okay, so no, this I will not come. I'm sorry. So this minus will also go. It will be like this: Q times this thing. Yeah? So it will not. So this will give you the total number of particles. Okay, so let me write. So type A particles Na, it will be like this thing: A dagger A, and type B type particles you will be having D3P B dagger P. Okay. Yeah. So now look here. So if let's say Q is the charge, okay, it is the unit of the charge on the particle. So the first quantity, it's a positive quantity. Clear? So you are having N, it comes with Q. Clear? So it will give me the total charge on the particle type A. And the second is having what? A minus sign. It will be minus, it will like this thing. Okay? So you are having therefore normal ordered charge operator, it will like this thing: Q times Na minus Q times Nb. So that means the charge on the particle type B is negative. It is actually opposite to that of charge of particle type A, and the total charge of the system is conserved. Clear? So samajh. Now let's say if you are having, if the particle is same as antiparticle, that means A is same as what? B. So if you are having A same as B, what this is? Zero. So you got the real field back. Got it? So now you can say if you are having a particle comes with a charge Q and its antiparticle is having charge with minus Q. Clear? And opposite charge. Or same amount opposite charge. Okay? Clear? Any question?